Edexcel Core Pure Polar Coordinates, sketching polar curves. When we're sketching polar curves, there are certain things we can use in order to make the sketch easier to draw. For example, we can think about the shape of the curve that we are sketching and important points on the curve. So usually these are points which are easy to calculate or significant values. When we're working out coordinates of points, we only usually need to look at a few key points on the curve and connect them together. Another useful thing to do is to think about how r changes for different values of theta. And the things that are particularly useful are when r reaches 0 or a maximum or a minimum, and the values of theta at which these key values of r occur. You can also use a graphical calculator if you have one available, and use the graphical calculator to display to help you produce the sketch. So here we have three polar curves that we'd like to sketch, and if you'd like to pause the video at this point, you may want to have a go at finding as many of the key features of these three curves as possible. So if first we consider the polar curve r equals 4. No matter what value of theta I choose, for example 0 or pi by 2, r will be 4. And r will remain 4. No matter which angle or direction I'm looking at, the value of r will be 4. So it seems sensible to sketch this polar curve as a circle, centre of the origin, radius r. And we'll have a quick look at this on a GeoGebra file now. And you can see no matter what position we choose for P, r is fixed at 4, and it's for any value of theta. And all that happens if we make the constant bigger is we get a circle of bigger radius. So now we're going to look at the polar curve r equals 3, 1 plus cos theta, and it's useful to have some values of theta which will give us some valuable information. For example, I'm going to use theta 0, pi by 3, pi by 2, 2 pi by 3 and pi, and I could choose others as well. And I usually choose values of theta which either give me important information about r or are easy to calculate. So in theta 0 we get r equals 6, at pi by 3 we get 4.5, at pi by 2 we get 3, at 2 pi by 3 we get 1.5, and at pi we get 0. Notice 6 is the maximum value of r and 0 is the minimum value of r. So when I'm pointing in the direction of 0, I am 6 units away. When I'm pointing at pi by 3, I am 4.5 units away. At pi by 2, 3 units away. At 2 pi by 3, I am 1.5 units away. And at pi 0. So we're starting to build up a picture of this curve like that. Notice also that cos theta is what we call an even function, which means that the cosine of minus theta will give us the same answer as the cosine of plus theta, which means we should have symmetry in the x-axis. So we should be able to plot points using this symmetry argument in order to complete the sketch. And we'll have a look at this in more detail on an autograph file. We're now going to watch autograph drawing this graph, and as we watch it, watch the angle theta sweeping around from 0 to 2 pi as it draws the distance r from the pole. So there we're nearly at theta's pi by 2, and there with theta's pi, and now we're sweeping past theta is pi to get the bottom half of the picture. So imagine him standing at the pole and facing in the direction of theta. Well, it may help you look for key features of the polar graph. So here is the sketch of r equals 3, 1 plus cos theta, and it's worth noting before we move on that if this was, for example, 3, 1 plus sine theta, then sine theta is a graph which is symmetrical about theta's pi by 2. In other words, the sketch would be symmetrical about the y-axis. So if you're looking for symmetry here, you would have symmetry about the y-axis. So now we're going to look at a sketch of the curve r equals 3 sine 2 theta, and again I've chosen some values of theta which are going to help us extract valuable information. 0, pi by 4, pi by 2, 3 pi by 4, and the value of pi. So using these values of theta, we get r equals 0, r equals 3, which is the maximum value of r we can get from 3 sine 2 theta, r equals 0, and this is the interesting one. When theta is 3 pi by 4, we actually get r equals minus 3, which is the minimum value, and we'll have a look at that in a bit more detail in a moment. And when we do pi, we are back at 0. So when theta is 0, we're at the pole. At pi by 4, our distance is 3, and at 0 we're back at the pole. So it's suggesting that if that's the maximum value, that we are creating some kind of a loop. What's interesting now is what this minus 3 would look like, and we'll investigate this using another autograph file. So again, we're going to watch autograph draw this curve slowly, and again take careful note of what happens to the distance r as theta sweeps round from 0 to 2 pi, but perhaps more significantly, notice what happens when r is negative. So that is the first loop, that's going from theta to pi by 2. Now notice that we've gone past pi by 2. It's now creating a negative value of r. So it's like walking backwards away from the pole instead of forwards. So now we've just gone past theta's pi, and r has gone back to being positive again. And now r is negative. So I'll just run that again so you can see it. So r is positive, r is negative, r is positive, r is negative, to give us the complete picture. And how much information you put onto your sketch will be dependent on the requirements of a particular question. But an awareness of r can be positive but sometimes negative would be very beneficial. So this is what the graph of r equals 3 sine 2 theta would look like if we did not distinguish between the positive and the negative values of r. But you should be aware that from theta 0 to pi by 2, and from theta is pi up to 3 pi by 2, then in those cases r was positive. And in the other cases, which is pi by 2 up to pi and 3 pi by 2 up to 2 pi, in those situations r would be negative. In the next video, we're going to be looking at converting between the two forms.